Okay, so now we're going to try some calculations to do with radioactivity. So this is all the maths that you need to know for P6. Before that, we need to remember some stuff about how we label elements. Now remember, the number at the top of an element is the mass number, and that's the number of protons plus the number of neutrons in the nucleus. Underneath, we have the atomic number. So here it's 6. And that's the number of protons. So it's also known as a proton number sometimes, the number of protons. So we get from the number of neutrons from that by simply minusing that from that. So here carbon has got 12 protons and neutrons, 6 of them are protons, so we know that 6 must be neutrons as well. Now knowing that, we can now label, we can think of this notation for these 3 particles, our alpha, beta and gamma particles. Now remember, an alpha particle is just a helium nucleus. So it's got 2 protons and 2 neutrons, 2p and 2n. So we label an alpha particle, we use the symbol alpha for the symbol there. Now the atomic number is the number of protons, we know there's 2 of those. The mass number is the number of protons and neutrons, 2 plus 2 is 4. So we can write alpha like this with alpha 4, 2. Beta is a bit harder because beta, remember, is a high speed electron, so it's an electron. I'm going to just write an E minus. So I'm going to use my symbol for beta, which goes here. My mass number is the number of protons and the number of neutrons. Now that is, by definition, 0. However, for the atomic number, this is why the rule doesn't hold particularly well here. It's the number of protons, and by convention, we say it's -1. We say that an electron's like a negative proton, although it really isn't, because that's something called an antiproton, but you don't need to know about that. So by convention, this is what we say for beta particles, okay, so you just need to remember that. So this is the alpha particles, 4 and 2. The beta particles we say -1 because it's an electron. Finally, we come to gamma. Now gamma, oh, I'll just drop the pen, there we go, I'll use a different one. Now gamma has the symbol, Greek symbol of gamma like this. The number of protons and neutrons is 0 because it's a wave. The number of protons is 0 because it's a wave. So this is my symbol for gamma, okay? Now because it's not a particle, it doesn't have any numbers on its label. So this is important because we're going to look at something called nuclear reactions or nuclear decay equations. Now, when a radioactive substance decays, it makes something new if it's an alpha or beta particle emitter. Now here I've got some radium, that's what Ra stands for, radium. This is what was discovered by Marie Curie, as is the next one. It decays into polonium by emitting an alpha particle. Now, if it decays into polonium, that means that the atomic number must have changed, because if it becomes a different element, this has to be different. Now, it's really important to remember that the number of protons and neutrons on one side, plus number of p plus n on one side, must equal the number of protons plus neutrons on the other side. So it doesn't change, okay? You can't get rid of them, they don't just disappear. So, if I look at that, the mass number tells me how many neutrons and protons there are. So I know that 200, I'm going to use different colours, pink, 222 must be equal to the mystery number here plus 4. And therefore I know that the mystery number must be 218. Because 218 plus 4 is 222. I'm going to change that to 218. Now the next number is 80, the atomic number. Now 86, this stays the same as well. It's going to be equal to something plus 2. So I know that that number there is going to have to be 84, because 84 plus 2 is 86. So the proper way to write this equation is that radium, 22286, becomes polonium, 2184, plus alpha, 42. And if you look along, 222 is equal to 218 plus 4, 86 is equal to 4 plus 2. Now exactly the same kind of thing applies for beta radiation. So this is alpha radiation. The exact same thing happens for beta radiation too. Except remember, with beta has this funny symbol where -1 is instead of a proton because we've got an electron there instead. So this here is lithium. And lithium, certain isotopes of lithium, decay into beryllium. I can never spell this one, beryllium, plus a beta particle. Okay, and you can see, it's easy to see on this one that we've got our protons and neutrons decaying into a different number of protons and neutrons and an electron. Now in beta decay, what actually happens is that one neutron becomes one proton plus one electron. It's not exactly the case that a neutron is a proton and electron joined together, but it's a nice way to think about it. So if you think of a neutron as kind of a proton and electron joined together, that's why it's neutral. It's not exactly right, but it's easy for nuclear decay equations. That makes it easier. The neutron splits apart into a proton and an electron. So the same rules as before apply. The mass number, this one here, has got to stay the same. So 8 is equal to a number plus, we can see that as 0. Now we know that if that's the case, question mark must equal 8. Because the number of protons and neutrons doesn't change and there's no difference for a beta particle. Now the second one is the atomic number. That's in orange. And there 3 must equal something minus, well plus, minus 1. Because our atomic number here is minus 1. This is where it gets a little bit harder. So 3 is equal to something minus 1, because remember plus and a minus is a minus. So that number must be equal to 4. So the proper way to write this decay equation is that 8,3 lithium becomes 8,4 beryllium, and we know it's changed element because its atomic number is changed, plus 0 minus 1 beta. So that's all there is to nuclear decay equations. You just have to make sure that the top line of numbers adds up, the bottom line of numbers adds up. You also need to know that beta is 0 minus 1 and that alpha is 4 too. If you know that, you should be absolutely fine with all of them. So if we think about the first decay we talked about, which was radium into polonium, we've got the right equation here by alpha particles. Now remember, radioactivity is something called spontaneous. Okay, it happens randomly. You can never say that atom or that nucleus, even is going to emit an alpha particle in exactly 10 seconds. We don't know, it's completely random. However, statistics wise, we can work out some statistics from it. Now if I start off with 100 grams of radium, now it will eventually decay all the way down. So by the time it's half its decayed, so I have 50 grams of radium and 50 grams of polonium. This takes 24 days to happen. It takes 24 days for half of the radium to decay into polonium. Now in another 24 days, it's not going to be that 50 grams of radium have decayed again. Half this will have decayed again. So in another 24 days, I'm now going to have 25 grams of radium plus 75 grams of polonium, because I've now got the 50 plus this new 25. You can probably see where this is going. In another 24 days, I now have 12.5 grams of radium left, and I have 87.5 grams of polonium. So every 24 days, half of that radium has decayed. And that's, for that reason, 24 days is the half-life, or T1 half, of radium. So the half-life of something is how long it takes, time it takes, for half the sample to decay. So if I now draw a graph of this, if I put here amount of radium in grams, and I put here time, and I draw 24, 48, 72. This is 0, and I have here 100, that must be 50 there, 25, 12.5. It's not well drawn, sorry. If I plot this, on my first day I had 100 grams of radium. I'm going to plot it in a different colour. My first day at 0, I had 100 grams of radium. 24 days later, I only had 50, so I'm going to get across here. Another 24 days later, I only had 25, I'm going to go across here. You're going to see the pattern. So what we get, if I join these all together, we get a curve. Okay, in this curve, you'll often see this is the half-life curve. Okay, it shows you the half-life of a material. Now, we can also measure radiation, or how much there is, by the count rate. If you hold a Geiger counter over the radiation, the number of times it clicks per second will be a lot higher when there's more of it. So at 100 grams will be, say, 10 counts every second, whereas when it gets to 50 grams, it'll be 5 counts every second. So the count rate halves as well. So I could also write up here, instead of that, count rate. And I get the same curve as we went along. So we can use one of these graphs to work out the half-life of the material. So if I have this material here, I can work out the half-life of it just using a graph. So here I've got counts per minute on this side and I've got time in minutes. Now it started off as 80, so the half-life is going to be when the counts per minute get down to 40. So if I go along to 40 and see what that line is, I go along there, I see that it gets to 2. So this is the half-life of this material. It's 2 minutes. The half-life of this material is 2 minutes. If I go to 4 minutes, I should see then that this is halved again, and that's exactly what I see. This is another, so that was one half-life, this is another half-life, and 2 minutes later it's halved again to 20. And this is a pattern that you'll always see. So another half-life, again, it's halved to 10. And it carries on and carries on and carries on. So that's how you work out the half-life of a material using a graph that looks something like this. There's 2 more things you might have to do with half-life. There's a few calculations. But they're quite simple numbers and you just have to work them out in your head most of the time. So the first one here, xenon is a radioactive gas with a use for diagnosing lung problems. In 15 days, activity falls to 1/8 of its original value. What's its half-life? So if it fell to 1/8 in 15 days, I know that in half of that time it must have been double that. So it got to a quarter in 7.5 days. And then if I double them all again, so it got to a half its original value in 3.75 days. So that means half the original value is what the half-life is. So the half-life of this must be 3.75 days. Another way they might ask this kind of question is like this. The half-life of a radioactive isotope sodium is 15 hours. A sample has a count rate of 240 counts per minute. Its count rate 60 hours later will be what? So at 0 hours, count is equal to 240. So at the half-life, which is 15 hours later, at 15 hours, I know that that count rate must have halved. So the count is now going to be equal to 120. Another half-life later, so at 30 hours, the count rate's halved again. So that's going to now be 60. So I know that if its count rate 60 hours, 30 hours later is going to be 60. Then it carries on and carries on. So at 45 hours, it's going to have gone to 30. And at 60 hours, it's going to have gone to 15. So at 60 hours, the count rate is 15 counts per minute. So it's lots of doubling and halving, these kind of questions. Now if you can cope with all of that math, that's all the math you need to know for P6. There's a lot more in P5 and P4, but for P6 it's much more kind of using your head and kind of thinking logically about it than using equations. So I hope that made some kind of sense. Fingers crossed.